us study the next topic, which is chemical properties of carbonyl compounds. We will see that all the chemical reactions exhibited by the aldehydes and ketones in form of a flowchart for easy memorization. So number one reaction is reaction with HCN, hydrogen cyanide. Now we know that the carbonyl group is polar, since we know that the oxygen is much more electronegative in comparison to carbon. So the carbon bears a partial positive charge and the oxygen bears a partial negative charge. So on treatment with HCN has hydrogen partial positive charge on hydrogen and partial negative on CN. So what will happen? It will result in the formation of cyanohydrins. Cyanohydrins bears negative CN will attach to the positive carbonyl carbon and positive H will attach to the negative oxygen of the carbonyl group. So the compounds formed are called cyanohydrins. Next reaction is reaction with sodium bisulfite or sodium hydrogen sulfide. Now with sodium bisulfite, it will result in the formation of the bisulfite adducts where SO3Na and OH will attach to the carbonyl carbon. Now these carbonyl compounds may be either aldehyde or may be ketone. Both of them will form bisulfite adducts on treatment with sodium hydrogen sulfide. Next reaction is reaction with alcohols. So with alcohols, if suppose it is an aldehyde, then it will result in the formation of hemiacetal. If it is a ketone, it will be named as hemiketal. Further, when another mole of alcohol will get attached, then the compounds formed will be called acetals. If the starting carbonyl is the aldehyde, it will be known as ketal if it is a ketone. So it will result in the formation of the hemiacetal or hemiketals followed by the formation of acetal or ketal reaction of alcohols with carbonyl compounds. Next is reaction with ammonia and its derivatives. These are very, very important reactions, and remember all of them are condensation reaction and involving the elimination of a water molecule. Now how water is being removed, the two hydrogens attached to the ammonia derivative and along with this carbonyl oxygen are being lost in form of water. So let us see first of all the reaction of any aldehyde with ammonia. With ammonia, this two hydrogens and this will be lost and it will result in the formation of Schiff's base. Schiff's base, which are actually we call them as imines also. These are also called imines. Next reaction is with hydroxylamine. Another ammonia derivative which is hydroxylamine NH2OH. So here this hydrogen along with this oxygen is lost in form of water and the compounds formed are called oxines. They are called oxines. Next reaction is with hydrazine. The formula is NH2NH2. Now all these reactions occur in the same way. Condensation reaction will occur and there will be elimination of water. For example, the two hydrogens attached to this nitrogen along with this oxygen will be lost in form of water and the resultant compounds formed, products formed are called hydrazones. So with hydrazine, they will form hydrazone no matter it is an aldehyde or it is a ketone. Now, this is hydrazine NH2NH2. If I replace one hydrogen of hydrazine by phenyl group, the compound will be named as phenylhydrazine. So let us see the reaction of phenylhydrazine with carbonyl compound. Again condensation, these two hydrogens along with this oxygen are being lost in form of water, resulting in the formation of compounds called phenylhydrazones. They will form phenylhydrazones. Next is to this benzene ring or the phenyl group, if I attach two nitro groups at number 2 and number 4, then my compound will become 2,4-dinitrophenylhydrazine, abbreviated as 2,4-DNPH, commonly known as, please note down, Brady's reagent. It is also called Brady's, B-R-A-D-Y, Brady's reagent. So 2,4-dinitrophenylhydrazine will form 2,4-dinitrophenylhydrazone, which will appear in form of an orange precipitate. So this reaction of any aldehyde or ketone with 2,4-DNPH, formation of orange PPT of 2,4-dinitrophenyl hydrozones confirms the presence of carbonyl functional group. So this is a characteristic test of carbonyl functional group, and the name of the test is Brady's reagent test, where we get an orange PPT of 2,4-dinitrophenyl hydrazone, irrespective of the fact whether the carbonyl compound is an aldehyde or it is a ketone. Both will give orange precipitate. Next is semi-carbazide. The formula is NH2NHCONH2. This is semi-carbazide, and again condensation will occur. It will result in the formation of semi-carbazones. This is semi-carbazone, the product which is formed by treatment of carbonyl compound with semi-carbazide is called semi-carbazone. Now, one more question comes related to this, that there are two NH2 groups here. In the semi-carbazide reagent, two NH2 groups are there, but only one is involved in condensation or removal of water. Why not this one? This one can't be involved because this is in conjugation with C double bond O group. So the lone pair on nitrogen is involved in resonance. Hence, from here H2 cannot be removed, since there will appear a positive charge of nitrogen on account of resonance. Therefore, only this side, the NH2 group of this side, removes water and results in the formation of semi-carbazones. Next are two very important reactions which have already been discussed earlier also. Let us revise them once again. Reduction. Now, reduction of any carbonyl compound using zinc amalgam and concentrated HCl will result in the formation of alkane, corresponding alkane, containing the same number of carbon atom as the parent carbonyl compound. It may be aldehyde. For example, it is ethanol, we will get ethane. For example, it is propanone, we will get propane. That means the carbon number remains same, it remains retained, and we will get alkane, the corresponding alkane, as a result of treatment with zinc amalgam and concentrated HCl. This reaction is called Clemenson's reduction. Next is another type of reduction which is called Wolff-Kishner reduction, another name reaction. The reagents are hydrazine, KOH and ethylene glycol. In the presence of hydrazine, KOH and ethylene glycol, again we can get alkanes, or again the carbonyl compound get reduced to alkanes. The reaction is called Wolff-Kishner reduction. Now just look at this part also. This is reduction. Reduction using lithium aluminium hydride as the reducing agent will reduce the aldehyde or ketones to corresponding alcohols. If it is an aldehyde, 1 degree alcohol will be formed. If it is a ketone, 2 degree alcohol will be formed. If you use an oxidizing agent K2Cr2O7 in the presence of H+, then we can convert or oxidize the carbonyl compounds to corresponding carboxylic acids. So learn this flowchart thoroughly, and all these reactions are very, very important. Now let us now proceed to the next topic, and that is miscellaneous reactions of aldehydes and ketones. Reaction with Tollens reagent. Tollens reagent, as discussed earlier, is called ammonical silver nitrate. It has been discussed in the video lecture 1.1 in the chemical test of distinction. So ammonical silver nitrate is a mild oxidizing agent and can be used as a test to distinguish between a pair of compounds, one aldehyde and another ketone. So when you treat any aldehyde with Tollens reagent, ammonical silver nitrate, then this aldehyde gets oxidized to carboxylic acid, and a shiny silver mirror is produced on the walls of the test tube along with the byproducts ammonia and water. So this test will be specifically or exclusively given by aldehydes. The reason being that aldehyde group is terminal, whereas ketonic group being subterminal does not act upon by the mild oxidizing agent. Next is reaction with Fehling solution. Felling solution is a mixture of felling A, which is aqueous copper sulfate, felling B, which is alkaline solution of Rochelle salt. Rochelle salt is sodium potassium tartrate. So these ions come from felling A and these comes from felling B. So when felling A and felling B are mixed to a sample of aldehyde, aldehyde gets oxidized to acid since felling solution is again a mild oxidizing agent. And it produces a red PPT of cuprous oxide Cu2O along with the byproduct water. Again remember, this is a chemical test to distinguish between aldehyde and ketone given by aldehydes, not by subterminal ketones. Again remember that felling solution also is a mild oxidizing agent. One more thing I want to tell you, add on here, is the felling test may be a distinction test between the aliphatic aldehydes versus aromatic aldehydes. Aromatic aldehydes, being resonance stabilized, do not react with felling solution. But aliphatic aldehydes can readily react and form a red PPT of Cu2. Next reaction is very important reaction called aldol condensation. First of all, let me tell you that this reaction is given by only those aldehydes or ketones which contain alpha hydrogen. Alpha hydrogens are the hydrogens attached to alpha carbon, and alpha carbon is the carbon adjacent to the functional group. So you can see this is the self-aldol condensation of ethanol we are discussing. So it is containing alpha hydrogen. So when 2 moles of ethanol are treated with dilute NaOH, look here, the alpha hydrogen of the second molecule of ethanol migrates to the carbonyl oxygen and converts it into OH. Now at beta position, we have the OH group attached. So these compounds intermediate which are formed are called aldols. Aldol is a combination of 2 terms, and ALD for aldehyde, OL for alcohol. So you can see alcohol in addition to the aldehyde. So the intermediate compounds are called aldols, which when heated will remove a molecule of water from the alpha and beta carbons. From beta OH is lost, from alpha H is lost, and water is removed so that a double bond is introduced, resulting in the formation of alpha beta unsaturated aldehydes or ketones. So this is a very important reaction called aldol condensation. Let me just recall the name of but-2-enol. Trivial name is crotonaldehyde. So if a question comes, how will you convert acetaldehyde to crotonaldehyde? It should click at once in your mind that we can apply aldol condensation. Remember, it occurs in the presence of aqueous alkali or dilute NaOH or dilute KOH. Next and last reaction of this is the Cannizzaro reaction. Cannizzaro reaction is a type of disproportionation reaction and is given by those compounds which do not contain any alpha hydrogen. So when, for example, formaldehyde, if you see, there is no alpha carbon, no alpha hydrogen. When treated with concentrated alkali or concentrated NaOH, will give you 2 products. One is the reduction product, that is alcohol, and another is the oxidation product, that is salt of carboxylic acid. So here you get methanol along with sodium methanoate or sodium formate as a result of Cannizzaro reaction of formaldehyde. Let us take another example, benzaldehyde. Benzaldehyde also does not have any alpha hydrogen. So when treated with concentrated NaOH, it will form 2 products, benzyl alcohol and sodium benzoate. So this is Cannizzaro reaction, again a very important reaction. Now we will move towards the next part, last part of the chapter, and that is carboxylic acids. Let us now discuss the last part of the chapter, that is carboxylic acids. Methods of preparation of carboxylic acid. By oxidation of primary alcohols and aldehydes. If we oxidize the primary alcohol using the strong oxidizing agents like KMnO4 acidified or K2Cl7 acidified, we can convert them into carboxylic acid. So just see 1 degree alcohol we have taken, subjected to acidified KMnO4, which is a strong oxidizing agent, we get carboxylic acid. In the same manner, we can also take aldehydes. Aldehyde group is also a terminal functional group, or maybe ketone. Aldehydes or ketones, both of them, on treatment with K2Cr2O7 acidified or KMnO4 acidified, will convert into carboxylic acid. So by oxidation of either primary alcohols or aldehydes, we can prepare carboxylic acid. Next is the complete hydrolysis of cyanides. We have already studied in the unit haloalkanes that cyanides on complete hydrolysis will give carboxylic acid. Partial hydrolysis in basic medium, they will convert into acetamide, but by complete hydrolysis, they can convert into carboxylic acid. So another way of preparing carboxylic acid is by complete hydrolysis of cyanides or nitrites. Next is from Grignard reagent. This is very important reaction. From Grignard reagent by reaction with carbon dioxide. So let me take a Grignard reagent. Any Grignard reagent we can take CH3NGBr, and when we treat it with CO2 carbon dioxide, then again the same mechanism is followed. The negative part of the Grignard attaches to the positive carbon of the CO2, followed by hydrolysis so that it will convert into the ethanoic acid, carboxylic acid, and again it is an ascent up reaction. You can see the acid obtained is containing greater number of carbon atom in comparison to the parent Grignard or the carbon dioxide. If we have to prepare benzoic acid by this reaction, then instead of alkyl magnesium bromide, we'll have to take phenyl magnesium halide and treat it with CO2 followed by hydrolysis so that we can get benzoic acid C6H5COOH. So this is very important reaction. Treatment of Grignard reagent with carbon dioxide. Next is, just now we have discussed in the previous lectures that if you hydrolyze any acid derivative, you can convert them back to parent carboxylic acid. For example, esters on hydrolysis in acidic medium will form carboxylic acid along with alcohol. Acetamides on hydrolysis will form carboxylic acid along with byproduct ammonia. Acid chloride on hydrolysis will form carboxylic acid along with HCl. And acid anhydride on hydrolysis will convert to form carboxylic acid. So all the acid derivatives on hydrolysis will give back carboxylic acid. Now let's see how can we prepare benzoic acid from toluene. Very important reaction again. Toluene when treated with alkaline KMnO4 called Bayer's reagent followed by heat, it converts into the potassium salt of carboxylic acid, which on hydrolysis can be converted to carboxylic acid. Here one thing has to be noted that not only toluene but alkyl substituted arenes, no matter however long is the alkyl side chain attached to the benzene ring, the product formed will be carboxylic acid. Because the carbon directly attached to the benzene ring gets oxidized and will give you carboxylic acid irrespective of the length of the alkyl side chain attached to the benzene ring. So toluene can be converted to benzoic acid. This is a very important method of preparation of benzoic acid. Now let us now see physical properties. Again, two properties we will be discussing in detail, that is the boiling point and the solubility. Now, if you compare the boiling point of carboxylic acid, maybe with alkanes, with carbonyl compounds, aldehyde ketones, with haloalkanes, with amines, with alcohols, you will find that the carboxylic acid have the maximum or the highest boiling points. The reason is they form extensive H bond which results in dimer formation. Dimeric association, the two molecules of carboxylic acid are held together by intermolecular hydrogen bond resulting in the formation of dimers, due to which they have very high values of boiling point, even higher than any other class of organic compound. Next, let's talk of solubility. Solubility, since they again will form H bond readily with water, hence they will be completely soluble or miscible in water. But aromatic acids will be insoluble in water or they will be sparingly soluble, since the bulky aryl group will offer steric hindrance in the formation of intermolecular H bond with water. Now let us see the chemical properties, and let us see the very important property, which is the acidity of carboxylic acids. We all know that carboxylic acids are acidic in nature. They will readily release H plus ion, and by the release of H plus ion, they can convert into a more resonance stabilized carboxylate ion. Let us look at the resonating structures of carboxylate ion, which is formed as a result of loss of H plus from carboxylic acid. So here, if you just see, you will find that the negative charge is delocalized on two highly electronegative oxygen atoms. And remember, greater the delocalization or dispersal of charge, higher is the stability. So these two structures are just similar to each other. So we say that these carboxylate ion exhibit the phenomena of equivalent resonance. And hence carboxylic acid very readily lose H plus ion and convert into more resonance stabilized carboxylate ion. Hence they are highly acidic in nature. Now let us see that what is the effect of substituents on the acidity of carboxylic acid. Substituents are actually of two types: electron donating groups and electron withdrawing groups. Donating groups, which tend to exert the plus M or plus R effect, and withdrawing groups, which tend to exert minus M or minus R effect. Donating groups will decrease the acidity, that means decrease the Ka dissociation constant of acid, but will increase the pKa. pKa is inversely proportional to Ka. And remember, Ka is the measure of strength of an acid. Stronger the acid, greater will be the Ka. Greater the Ka, lesser will be the pKa. So electron withdrawing groups, for example, just see, nitro group is electron withdrawing, but methyl group is electron donating. So if you are asked to compare or arrange these three sets of compounds in the increasing order of their acidity, then remember that withdrawing groups will increase the acidity and donating groups will decrease the acidity. Next factor affecting acidity is the electronegativity of the halogen. Electronegativity of the halogen is directly proportional to acidity. That means if we have fluoroacetic acid, it will be more stronger acid in comparison to chloroacetic acid, in comparison to bromoacetic acid, in comparison to iodoacetic acid. So with the increase in electronegativity of halogen, the acidity increases. Number of electron withdrawing groups is directly proportional to acidity. That means greater the number of halogens, suppose, attached. If you compare the acidity of trichloroacetic acid with dichloroacetic acid and monochloroacetic acid, you will find that trichloroacetic acid has the maximum acidity. So these were the factors affecting the acidity of carboxylic acids. Let us now study the chemical properties of carboxylic acids. First of all, reactions involving we will study the properties of carboxylic acid in the three categories. Reaction involving the cleavage of O-H bond, reaction involving the cleavage of C-O bond, and reactions involving the COOH group as the whole. So let us start with the very first property, reactions involving the cleavage of O-H bond, responsible for the acidity of carboxylic acid. So with four different reagents, let us see. With Na, that is electropositive sodium metal, the acidic hydrogen of carboxylic acid gets replaced by sodium, forming sodium carboxylate, resulting in the evolution of a hydrogen gas which burns with a pop sound. In the same manner, on treatment with NaOH, it again forms sodium carboxylate along with the formation of the byproduct water. Now, with sodium hydrogen carbonate, that is sodium bicarbonate or sodium carbonate, with both of them, a brisk effervescence of a colorless, odorless carbon dioxide gas is evolved, which when passed through lime water will turn lime water milky. So reaction with sodium bicarbonate or sodium carbonate resulting in the evolution of CO2 gas is the characteristic test for carboxylic acids. Remember, not given by phenols, given by only carboxylic acids. So, these were the reactions involving the cleavage of O-H bond. Now let us study the reactions involving the cleavage of C-O bond of the carboxylic acid, and all these reactions we have already studied earlier in the introductory part of the chapter, which basically result in the formation of the derivatives of acids. For example, let us see them once again. For example, if carboxylic acid are treated with alcohol in the presence of H2SO4 acting as a dehydrating agent, it results in the formation of pleasant fruity smelling compounds called esters. RCOR is formed. Then if you treat it with ammonia, carboxylic acid, then ammonium salts will be formed, which after elimination of water on being heated will convert into another acid derivative called acid amide. On treatment with PCl3, PCl5 or SoCl2 thionyl chloride, acids can be converted to acid chloride. And finally, on treatment with P2O5 and heating, P2O5 acts as a dehydrating agent. So water is removed in this reaction and it results in the formation of another acid derivative called acid anhydrides, alkanoic anhydrides. So all these reactions are the reactions involving the cleavage of C-O bond, resulting in the formation of derivatives of acids from carboxylic acid. Next is reactions involving COOH group on the whole. And we will see here three categories of reactions. First is the reduction, and reduction of any carboxylic acid using lithium aluminium hydride as the reducing agent will convert the carboxylic acid to alcohols. Remember, 1 degree alcohols will be obtained. Why only 1 degree? Since the COOH group is a terminal functional group. So as a result of reduction, the acids on treatment with lithium aluminium hydride will get reduced to corresponding 1 degree alcohols. Next reaction is decarboxylation, which means removal of carbon dioxide. And remember, the reagent for decarboxylation is soda lime. Soda lime, as the name suggests, is a mixture of caustic soda NaOH and quick lime CaO. It is a reagent responsible for removing carbon dioxide. So if we take sodium salt of any carboxylic acid, Na2CO3, CO2 will be lost in form of sodium carbonate, resulting in the formation of alkane containing 1 carbon less than the parent acid. So here you can see this is the acid and it converts into RH, which is actually having 1 carbon less than the parent acid. So it is also said to be a descent down reaction since it is decreasing or degrading the number of carbon atoms. Similarly, if we take sodium benzoate and treat it with soda lime, we can convert sodium benzoate into benzene along with the byproduct Na2CO3 is obtained. Next reaction we have already studied earlier and it is called HVZ reaction, stands for Hell-Vollard-Zelensky reaction. It is given by only those carboxylic acids which contain alpha hydrogen. This is alpha carbon, these are alpha hydrogens. So when you treat any carboxylic acid containing alpha hydrogen with halogen in the presence of red phosphorus, then the alpha hydrogen gets replaced by halogen, resulting in the formation of alpha halocarboxylic acid. Remember, formic acid will not give HVZ reaction. The reason being formic acid does not contain any alpha hydrogen. So HVZ is all about the replacement of alpha hydrogen of any carboxylic acid with halogen on treatment with X2 in the presence of red phosphorus. Now we come to the concluding part of the chapter, ring substitution or electrophilic substitution reactions of aromatic acids. For example, if you see benzoic acid and if we see the ring substitution reactions of benzoic acid, we have to keep in mind that the directing influence of the COOH group is that it is meta-directing. That means whatever electrophile of the reagent will attach at the meta position, resulting in the formation of a meta-substituted acid derivative. For example, if you subject it to nitration, treatment with nitrating mixture, HNO3 concentrated, H2SO4 concentrated, is collectively called nitrating mixture. So when you treat carboxylic acid, the nitronium ion electrophile gets substituted on the meta position, forming 3-nitrobenzoic acid. Similarly, sulfonation of this benzoic acid will convert it into, again, the SO3H electrophile will be attached at the meta position. In the same manner, if you treat it with, or if you subject it to bromination, Br2 in presence of FeBr3, then it will convert into 3-bromobenzoic acid, commonly called meta-bromobenzoic acid. So it will give you meta derivatives. Why? Because the directing influence of COOH group is that it is meta-directing, and remember it is deactivating also. So there is a 1-mark question, important question which comes in the exam. Benzoic acid does not undergo Friedel-Crafts reaction. In Friedel-Crafts reaction, we use the anhydrous AlCl3. The role of anhydrous AlCl3 is to act as a Lewis acid. And it does not undergo Friedel-Crafts reaction because the COOH group, just now we saw that it is deactivating group. And the anhydrous AlCl3, which acts as a Lewis acid, gets bonded to the deactivating carboxylic group, on account of which it cannot show Friedel-Crafts alkylation, neither can it show Friedel-Crafts acylation. So children, this is all about the chapter Aldehyde, Ketones and Carboxylic acids. Prepare this chapter thoroughly, do the conversions from the NCERT back exercise, and do all the important questions which have been there in the previous year board examination. Have a nice day.